Hello and welcome to this new tutorial. So now that we've tackled the creation of the LSTM cell and the dropout, time to wrap the whole thing, connecting all this to the inputs, the outputs and the target into the whole recurrent neural network model. And the way we're going to do this is we're going to create some TensorFlow placeholders for the input, the target and the output, meaning what will be returned by the RNN. And that's why I've prepared for you a new resource which will be useful for this tutorial, which is the TensorFlow placeholder function from the TensorFlow documentation. So let's have a look at this function. Let's have a look at what it does first. It inserts a placeholder for a tensor that will always be fed. And that means that the recurrent neural network that we will build expects a certain format of its input. And it will return the output in the same format as well. And therefore the target will need to have the same format when we compute the loss error between the output and the target. So it's super important that you know this, the TensorFlow placeholder, because it is the compulsory format to have when you are working with neural networks in general. So let's do this. Let's create the TensorFlow placeholder for our inputs, our target and our output, and we're going to start with the input. But first, we're going to do something very quick. We're going to create an object variable for that maximum sequence length, and that's because we're going to need it to create the placeholder. So let's do that quickly first. We're going to create a new object variable, self.sequence length, which will be equal exactly to that variable that is a simple variable and not an object variable. So we will paste that here, and then now is the time to create the placeholders. And we're going to start with the input placeholder, to create a tensor of input in the right format for the recurrent neural network. And we're going to call that input placeholder self.input x. And of course self dot because it needs to be an object variable. Then that's where we can call TensorFlow, and from TensorFlow we're going to call the placeholder function, here it is, to which we're going to input these three arguments. So first, the D type is simply the type of the values that will be in the cells of these tensors, and since these values are just the result of all the computations with all the normalization and everything, of course the D type is a TensorFlow float, and we can take the 32 one to have enough figures. So float 32, and then the next argument, well, we cannot see it anymore, but we can see it here. The next argument is the shape, and this will be exactly the shape of the tensors for the inputs, the targets, and the outputs. And these tensors are all going to have the same dimensions. The first one will correspond to the batch, so it will be the batch size. The second one will correspond to, well, exactly what we've just set as an object variable, the sequence length. And the third one will be the number of channels in the tensor, that is, its dimension. And that's what we gathered here first. Remember, when gathering the parameters, that's the dimension of the input in width, which remember corresponded to 35 channels, 32 for this first input here, the latent vector z, and 3 for this second input, the action. So 35 channels in total. And then for the out width, the dimension of the output will be 32, because this time it corresponds to the output of the MDN RNN that has 32 channels. So that's going to be the third element of this shape, and therefore that's exactly what we're going to input now. And so I'm adding the shape equals to these three dimensions that will enter in square brackets. The first one, as we said, corresponding to the batch size, in which we're going to get from our HPS object variable containing all the hyperparameters, from which we're going to get the batch size. Here we go. Then second dimension, this is, again, we can take it from our HPS parameter object, from which we're going to get the max sec len. That is exactly this one, HPS max sec length, or length, or even self.sequence length that we've just created. And the third one, as we said, the dimension of the input, which is in width, corresponding to 35 channels. Or, of course, we could have put self.hps.input sec width. All right, so good thing done. We created the TensorFlow placeholder for our input, meaning the right format of our input to be fed into the neural network. And now we're going to do the same for, this time, the target, which we will call this time output x. So I'm going to replace that in here by out, and then same, it's going to be a TensorFlow placeholder with a float32 type for its cells, then almost the same shape. We're going to have the same batch size, of course, the same maximum sequence length, of course, but the right dimension of the target, which is the same dimension as the output, that is out width, corresponding to 32 channels. So good, we have created our two TensorFlow placeholders for the input and the target. We will do the same later on for the output, meaning what will be returned by the RNN, but first we will take care now of gathering all the inputs that we'll need to create our final RNN, and which we will do with this dynamic RNN function. So let's have a look. What are the arguments of this dynamic RNN function? Well, the first one is the cell, and that we've already created. That was the LSTM cell, which we've created in the previous tutorial. Then these are going to be the inputs, and which again we have already created just now. But we're not going to enter this self.inputx because we will create a separate variable. It is safer when we do some further modifications of the input, and therefore we're just going to create a new variable here that we'll call actual input x, and which will be of course equal to the self.inputx object variable. And that's just to create separately a variable which will be exactly the input of this dynamic RNN function, that is this input argument here. Alright, so done for this one. Then sequence length. Well, since we've specified the sequence length in the input, then we don't have to specify it here, so we will just keep the non-default value. But then for the initial state, that's the next step here that we have to do. We have to initialize the state with all zeros as opposed to just inputting a none. So that's exactly what we're going to do here. We are going to create the initial state initialized with only zeros, but of course with the same batch size, because again, we're not going to get a single initial state, but we're going to create a batch of initial states. So let's create this new required argument initial state for our dynamic RNN function, which we will call self.initial state. And so that's going to be the initial state inside the LSTM cell. So we can just take our cell here, so copying this, pasting that here, and from which we're going to get one of the attributes of the layer norm basic LSTM cell, because I remind that cell is nothing else than cell fn here, and cell fn here is nothing else than an object of this layer norm basic LSTM cell class, and therefore from cell here we can get all the attributes of the layer norm basic LSTM cell. And right now the one we're interested in is the zero state function attribute, which will allow us to initialize the state with only zeros. And that's why, as I've just told you, we have to specify the batch size here because we're gathering a batch of initial states to be 100% aligned with our other formats of the input, the target, and the outputs. All right, so here we're going to enter a batch size argument as hps.batchsize. Here we go. So hps or self.hps, that's the same because hps is an argument of the init method. And then what is the other argument? We can no longer see it, but it was dtype again, and which of course will be again TensorFlow float32, the float32 type by TensorFlow. All right, perfect. We're getting very close to the final call of the dynamic RNN function, but first we have to take care of the output. And we actually have a lot of work to do on that because, remember that we have to distinguish two outputs, the deterministic output returned by the RNN only, and then the stochastic output returned by the MDN. And in order to create that stochastic output, well, we have to prepare now the tensors of weights and biases, which will be required for the MDN. Because indeed, the next step after getting that deterministic output of the RNN, well, what we'll do is do a matrix multiplication, and that's why I've prepared for you a function that we'll use soon, which is this matrix multiplication function xw plus b, which will multiply the deterministic output of the RNN by this tensor of weights that we're about to create, plus this tensor of biases that we're about to create as well, in order to get prepared for the stochastic operations by the MDN. And therefore, that's the important part of the work we have to do for the output. Right now we will create these two tensors of weights and biases, and now it's important to understand that the tensor of weight will be a matrix with RNN size, number of rows, and RNN size, remember, is the number of units we input here for the LSTM cell, which we've created with the layer norm basic LSTM cell class. So that is exactly going to be the number of rows in this matrix of weights. And then for the number of columns in this matrix of weights, we'll have 32 times 5 times 3 columns. And the reason for that is that the dimension of the weight that we'll need for each of the LSTM units is the multiplication of the dimensions of the two inputs that we have here, which are the action and the latent vector z. And this, remember, has a dimension of z size equals by default 32. This, the action, has a dimension of 3, because at each time we can play 3 possible actions and therefore a vector of 3 elements. But then let's not forget that we'll use 5 Gaussian mixtures, and therefore to get the total number of dimensions of the weight and therefore also the biases, we will need to multiply 32 here by 3 and by also 5, the total number of Gaussian mixtures. And therefore, let's get that second dimension of the tensor of weight in a separate variable here, which we will call n out, and which, as we said, is equal to the dimension of the output, out width, which I'm copying here, out width multiplied by the number of Gaussian mixtures, k-mix, and multiplied by 3, the dimension of the actions. And that is the second dimension we'll have in our tensor of weights, meaning the number of columns we'll have in our tensor of weights. And also, it will also be the total number of elements in the one-dimensional tensor of biases, because indeed, then what we'll do is, once we multiply the deterministic output of the RNN by the tensor of weights, well, we will add the biases, and therefore there will be the same n out number of biases. Alright, so now that we've computed this number, well, let's create these two tensors, and we're going to create them inside a TensorFlow variable scope, which will be exactly the variable scope used to build the RNN. And therefore, I'm introducing it now with the TensorFlow variable, here we go, scope, inside which we just have to input the name of the scope in quotes, which we'll call the RNN variable scope. And then inside, we're first going to define the 2D tensor of weight and the one-dimensional tensor of biases. So let's start with the tensor of weight. We're going to call that output W, and we will create it thanks to a TensorFlow function, which will be the get variable function, inside which we will input the name of that tensor, which will be, well, we can just call it again output W. And then, of course, here comes the most important argument, the shape, which is the shape we've just mentioned, that is, with the total number of LSTM units RNN size and n out number of columns. So here we go, let's input that shape here. We're going to input that in square brackets with the 2 dimensions. The first one is, as we said, self.hps, our hyperparameter container, from which we're going to get the RNN size. That's for the first dimension of the matrix of weights, the number of rows. And then for the second dimension, well, that's what we've just computed here, n out. And so here we go, we're going to have n out number of columns. And that's the dimensions of the matrix of weight, which we will multiply to the deterministic output of the RNN, so that we can get later on the stochastic MDN output layer. All right, so now we're going to take care of the other tensor for the biases, which will correspond, to the biases here. We just initialized that, and now we're about to initialize this, the biases, and therefore that's why I've copied this. I'm going to paste that just below. We're going to replace output W by output B for the biases, then same here, output W by output B. And now, however, we're not going to have a 2D tensor but a 1D tensor, which will of course have n out elements. So I'm just removing the first dimension, which was only for the weights, so that we only keep n out. And here we go. Now we have our 2 tensors of weights and biases, and so we are ready to get the deterministic output of the RNN. And then we'll be ready to compute the matrix multiplication of weights plus the biases, after which the mixture density network will come into play to get that final stochastic MDN output layer. So we'll do all this in the next couple of tutorials, and until then, enjoy AI.